Alright, welcome back everybody. In this video we're going to look at derivatives of vector-valued functions. We're going to start with some basic vector function notation and look at a few examples along the way. Alright, so any vector that we have, it says here, can be written as a linear combination of the two standard unit vectors, I, which is the vector 1, 0, and j, which is the vector 0, 1. So for instance, the vector 3, negative 2 in vector function notation can be written as 3i minus 2j. Alright, let's look at example 1. We want to write the vector pq as a linear combination of I and j. So first we figure out what the vector pq is. Its x component goes from negative 2 to 4. So its x component is going to be 6. And its y component travels from 5 to 3. So its y component is going to be negative 2. To write this as a linear combination of the standard unit vectors, this is going to be 6i minus 2j. And there is your standard vector for this particular vector pq. Alright, we talk a little bit about some vocabulary. Make sure you read through that and you're familiar with all of these terms. When we graph a vector-valued function on our graphing calculator, we're going to graph it the same way we did a parametric function. What we need to visualize, though, with a vector-valued function is we need to visualize that this function is just showing the movement of the tip of the vector. So what you'll see is you'll see the motion from the tip of one vector to the next. As the function moves around, we've got all these vectors streaming out to this path. Alright, let's look at this. We're going to look at the vector-valued function r of t equals t cosine of ti plus t sine of tj. We'll look at this on our calculator. So in order to look at this graph, we want to be in parametric mode. We're going to type in the function t cosine of t is our x component, and t sine of t is our y component. Alright, now to actually see what's going on, I want to set this to path, because then we will see, that's the little line with the bead, that's our path graph. What we'll see is we'll see the tip of the vector moving around, and it'll leave behind the path of the vector. Alright, now in order to see this best, we're going to change our window values. Let's see, 0 to 50. By the way, I went through and selected these window values in advance so that we could best see the path of this vector-valued function. Max 20, and my y scale is 2. Alright, and now we're going to graph this, and you'll see the tip of the vectors as this vector-valued function moves around the coordinate plane. And so you see this ball moving along here, and all that's showing you is it's showing you the tip of a vector as it moves around. And it's leaving behind the path of what's going on here with the graph of t cosine of t, t sine of t. This is a perfect opportunity for me to take a sip of my water. And basically what we see is we just see it moving along, and it's tracing the tip of the vectors as it moves along in that particular direction. Oh boy, you know what? That's not showing me the graph that I want, because I'm still in degree mode. I want to be in radian mode. Alright, let's try this again. This is going to be a more interesting graph than that last one that we saw when it was in degree mode. Now we're seeing the tip of the vectors for this function. Yeah, there we go. And basically, we've got this vector that's moving around the axis, and it's gradually getting further and further from the center. And as we see the path left behind by the tips of these vectors, we see it creating this spiral shape. I wish I had not forgotten to change it out of degree mode initially. And there you see the graph of this vector valued function, and what you see left behind is a tracing of the tip of the vectors that are spiraling around the origin in this context. Alright, that was pretty cool. Alright, a definition of limits for vector valued functions. If I have a vector valued function, r of t equals f of t I plus g of t j, if the limit as t approaches c of f of t is L1, and the limit as t approaches c of g of t is L2, the limit of the vector valued function is just those individual limits times the standard unit vectors. So if we want to find the limit as t approaches 2 of r of t for this function, we're going to find the limit as t approaches 2 of the coefficient of the I vector, which that approaches 4. And the limit as t approaches 2 of the coefficient of the j vector, that approaches 5. And so the limit of this vector valued function as t approaches 2 is the vector 4i plus 5j. Alright, we talk a little bit about continuity. In order to be continuous, the limit as t approaches c of the vector valued function needs to be the same as the vector valued function evaluated at that point. Whole lot more there. Component test for continuity, make sure you read through that. The derivative of a vector valued function. This is very simple when we have the vector valued function f of ti plus g of tj. In order to find its derivative, dr dt, which is a vector derivative, we're going to just take the derivative of the I component and multiply it times I, and the derivative of the j component and multiply it by j, and that gives us the derivative of this vector valued function. So dr dt here, notice I have my vector symbol above the r because r is a vector, but not above t because t time is a scalar here. I want to take the derivative of this first component. The derivative of 1 over t squared plus 1 is going to be negative 2t over the quantity t squared plus 1 quantity squared. That's times I plus, and now the derivative of this other component, oh golly, let's see, that's t times t squared plus 1 to the 1/2. Using the product rule, we end up with t squared plus 1 to the 1/2 plus t times 1/2 t squared plus 1 to the negative 1/2 times 2t. So it ends up being square root of t squared plus 1 plus, oh crap, come on Thomas, I'm taking the derivative of the wrong thing. That's a t squared plus 1 to the negative 1/2 initially. And so we've got t squared plus 1 to the negative 1/2 plus t times negative 1/2 t squared plus 1 to the negative 3/2 times 2t. And so we've got 1 over the square root of t squared plus 1 minus t squared over t squared plus 1 to the 3/2. Getting that over the common denominator, t squared plus 1 to the 3/2. We multiply the first fraction here by t squared plus 1 over t squared plus 1. So this turns into t squared plus 1 minus t squared. And so it ends up just being 1 over quantity t squared plus 1 to the 3/2 j. And there's the derivative of that vector-valued function. Alright, that's where we're going to stop for this video, and we'll see you guys next time where we finish this lesson and look at examples 4 and 5. Alright, see you then. Have a great rest of your day.